بسم الله الرحمن الرحيم. As you see in chapter 1, we solved actually the problem of solution of system of equations, and which can be written in the form ax equal b. In chapter 2, we are going to solve again this equation, but in different ways. Okay. And we will concentrate on this case of unique solution. Okay, so we are going to find, for example, what is called the inverse of a matrix. To find the inverse of a matrix, we first would like to define some operation on matrices. So we'll begin with addition and subtraction, scalar multiplication, matrix multiplication, and transpose of a matrix, trace of a matrix, and some special matrices. This is for today, inshallah. The next lecture, we are going to define the determinant and see the relation between the determinant and the matrix. And the following lecture, we are going to get the inverse of the matrix. Okay? So let's first introduce some operation on matrices. And as you see, a matrix is actually a rectangular table of numbers arranged in rows and columns, as you see in chapter 1. And we write actually here the dimension of the matrix. So for example, this matrix has 2 rows and 3 columns, so we write the dimension as 2 by 3 matrix. If the number of columns equals the number of rows of a matrix, we call this matrix a square matrix. Okay? So this is a general rectangular matrix, and if you have m equal n, the 2 numbers are equal here, so we call it a square matrix. And as you see also in chapter 1, we can write the matrix in symbol notation. We usually use the capital letters for the matrix, big A, and the small letter A for the entries of the matrix. So this guy, for example, this is the element in the first row and the jth column. Okay? So these are the elements of the jth column, and these guys are the elements of row I. So this is AI1, AI2, and so on up to AIN. If I want to define the addition and subtraction of 2 matrices, what do you expect to be the condition for the addition to be valid for 2 matrices? If I want to add 2 matrices, they must have the same dimension. The same dimension, okay? That's the same shape. And to add 2 matrices, you simply add the corresponding entries. Okay? So for example, if I want to add these 2 matrices, the sum would be, the first element would be 7, and then 5 and 9 and 3. So this is simply the addition or subtraction of 2 matrices. Just add or subtract the corresponding entries. Let's define the scalar multiplication. If I want to multiply a matrix by a number, okay? This is called the scalar multiplication. So to multiply this matrix by k, so simply multiply each entry in the matrix by this k. And notice that this would be different from scalar multiplication for the determinants, which we are going to talk about the next lecture. For matrices, we multiply each entry by this scalar. So for example, if you have 3 times this matrix, so the output would be 6, 3, 12, and 15. Okay. If you remember, in chapter 1, we multiply the matrix by a vector, if you remember. So if, for example, I want to multiply the matrix A, 2, 3, 1, negative 5 by the vector 4 and 1. According to the definition, the output would be a linear combination of the columns of A using these guys as combination weights. So this guy is 4 times the first column plus 1 times the second column, right? Which is going to be 8 plus 3, which is 11, 4 minus 5, which is negative 1. So this is how to do matrix vector multiplication. Let's extend this definition if you have matrix multiplication. So I write the matrix B as the augmentation of several vectors. So assume B is the augmentation of these columns. And if you want to multiply A by this matrix B, if I want to multiply A by the matrix B, I write B as B1, B2, B3 as vectors. And multiply the matrix A by each column in B, or each vector. So we'll get AB1, which is this guy, okay, and AB2, and AB3. And then augment these guys to be the product of the matrix A by the matrix B. So if I want to do it in this example, so I multiply A by the first vector, A by the second, A by the third. Okay, so this is the first one, which I did in the board. You do the same for the second one, multiply A by the second column here. Do the linear combination, get your output. Repeat for the third column of B, and then augment these guys together to get the product of AB. Okay? Do you have a condition here for the multiplication to be valid? Is there a condition? Let's get back to this guy. When you do this multiplication, we say we do actually linear combination of these guys using these entries as combination weights. So the number of columns here must be equal to the number of rows in the vector, okay? So this is going to be applied also for matrix multiplication. So the formal definition for matrix multiplication, if you want to multiply matrix A by matrix B, so there is a condition on the dimension here, which is the number of columns of the left matrix must be equal to the number of rows of the right matrix. Okay, so we have a left and right matrices. The number of columns of the left matrix equal to the number of rows in the right matrix. And the definition of AB, as we said, is to write the matrix B as augmentation of some columns or some vectors, and then multiply A by each vector, and then augment the output. What is the dimension of AB? Actually, the dimension of AB would be M by P. M by P. This is the dimension of the resultant matrix. Okay? So in the previous example, let's see it here. If I want to multiply these guys together, 2 by 2 matrix by 2 by 3, so this is the condition. These guys must be equal. And the dimension of the resultant matrix would be 2 by 3. If you remember, also in chapter 1, we did the multiplication in another way called row vector rule. So instead of doing linear combination between the columns of A using the entries of B, so you can do it in another way, is to do row vector rule. Do you remember the row vector rule? you simply do what? Do dot product between the first row here with this vector. So doing the dot product, you will get 4 by 2 plus 3 by 1, which is your 11. So this is 4 by 2 plus 3 by 1. And then get the second entry as the dot product between the second row of the left matrix multiplied by your vector. So we'll get 1 by 4 minus 5 by 1, which is your negative 1. So this is another way to get the matrix vector multiplication. So actually you can extend this for matrix multiplication. If I want to do this multiplication using the row vector rule, so I'll take this row and multiply it by the first column here to get the first entry. And then multiply this row by the second column to get the second entry, and so on. So let's see it. So first write the output dimension, which is 2 by 3. These guys multiplied. And then multiply this row by this column, dot product, get the first entry. And then move to the second column. Take the first row from the left with the second column of the right matrix and do the multiplication. So we'll get here 2 by 3 plus 3 by negative 2. And then move to the third column, which is 2 by 6 plus 3 by 3. And then move to the second row to fill here the second row. So take the second row with each column and do a repeat. You'll get these guys. Simplify to get your output. Okay? So we have two ways to find the matrix multiplication. Either to do matrix vector multiplication using linear combination and then augment with each one, or using the row vector rule with each entry. So we'll have dot product for each entry. Okay, we usually use the row vector, but on computer it's better to use the linear combination, which is faster. Okay? Suppose that I want to find a specific entry on the output matrix. I don't want to evaluate all the entries of the output matrix. I just want to find this guy, the first element in the first row and the third column. How to get this guy? Take from the left matrix the first row and multiply it by the third column and do the row vector rule. So I'm going to do dot product between 2 and 3 vector with the vector 6 and 3, right? In general, if I want to find the entry in the I row and j column of the output matrix, so what do we do? I'm going to do dot product between row I in matrix A, dot product with column J in matrix B. Okay? So we write it this way. Row I of matrix A and multiplied by dot product with column J of matrix B, which we usually write it as Bj. So dimension-wise, can you multiply these matrices together? Dimension-wise, can you do this multiplication?
No.
Let's write the dimension of A and B and check. Dimension of A is 3 by 5, and this guy is 5 by something, so the multiplication is valid. And the output matrix has a dimension of 3 by 2. Okay? So first write the dimension. So here 3 by 5, and this guy is 5 by 2. These guys are matched. And the dimension of the output matrix is 3 by 2. Okay? So to summarize, if you have A and B, and A has a dimension m by n, and B has a dimension p by q. So AB exists only if now condition واحد, one condition, n equal p. This guy must be equal to this guy. Okay, the number of columns of the left matrix equal the number of rows of the right matrix, and the dimension of AB is m by q. Okay, if you want the entry ij, as we said, we do the dot product between row I in A with column j in B. So what are the entries of row I of A? If I want to write it in a symbolic notation, what is row I in matrix A? The entries are A, I, 1, and then A, I, 2, and so on. These are the entries of row I in matrix A. What are the entries of column J in matrix B? B, 1J, B, 2J, entry in the first row and jth column, and so on. So we're going to do dot product between these guys. Okay? So A, B, the entry indexed I and J equal to AI1. I'm going to do dot product. Okay? AI1, B1J plus AI2, B2J, and so on. Right? Okay. To write it in a compact form, we write it this way. Summation AIK, BKJ, and K loops from 1 to n. So you have for loop to find the value of each entry in the product. Okay, for loop to find the dot product. Okay. Okay. يعني على الكمبيوتر انا هعمل ايه؟ هعمل for loop to find the entry indexed at I and J. for loop عشان تلوب for k من 1 to n. نعمل for loop وتاخد في كل مره تاخد number من A ونمبر من B وتعمل multiplication وتفضل sum up لغايه ما اجيب ال value of this n. طب let's try an example. Let's find AB and BA for these matrices. To find AB, you have to write A to the left and B to the right, okay? So write A to the left and B to the right and do the multiplication. So if I want to apply the row vector rule, for example, so the first entry would be dot product between this row vector and this column vector. So it would be 1 by 2 plus 3 by 0, which is 2. The second entry to the right, the first row, I'm going to do dot product between this row vector and this column vector. So we'll get negative 1 plus 6, which is 5. Okay? Is this right? Okay? What about BA? Again, I have to write B to the left and A to the right and do the multiplication. What about the first entry? These guys dot product. So we'll get 2 minus 2, which is 0. Okay? The second entry to the right, you'll get 6 plus 1, which is 7, and so on. So what did you notice about the result of these two products? AB doesn't equal to BA. So in general, in matrices, the multiplication is not commutative. Okay, so be careful when you find AB or BA. They are not necessarily the same. Okay, so we say that multiplication is not commutative in matrices. What about these guys? Let's find AB for this example. Okay. So I'm going to write A to the left, B to the right. What about the first entry? 3 minus 3, which is 0. The second, 6 minus 6, which is 0. 6 minus 6, 0. 12 minus 12, 0. So do you have any comment about the result here? Look at this matrix. Do you have any property for this matrix? في some dependence between الكولمز بتاعها. ان الكولم ده هو multiple من الكولم ده. اوكي طيب احنا هنقول الكونديشن ده ان في بعض البروبلمز you will find that AB equal to 0 and this does not imply in general in A equals 0 or B equals 0. Later on we'll see when this guy implies this condition. But for now, this guy does not necessarily imply that any of them must be 0. Okay? We'll see later on what is the condition on A and B to have the case of one of them must be 0. For this example, I have A and B, and I want to find these guys. A plus B power 2, and A squared plus 2AB plus B squared. Let's first define the power of a matrix. We define, for example, A power 2 as the product of A by itself. So we'll do matrix multiplication, multiply A by itself. See, if I want to find A plus B all square, so I'll find the sum first of A and B, and then multiply it by itself. So this is A plus B. Okay, this is A plus B, and I multiply it by itself to get A plus B squared. If you do here the multiplication, you will get this matrix. If I want to find the second requirement, A squared plus 2AB plus B squared, so first I'll find A squared as A by itself, B squared B by itself, 2AB, I'm going to multiply A by B and then do scalar multiplication by the value of 2 for each entry of AB. If you do this, you are going to get this answer. So what did you notice in the result of these two values? A plus B all square and A squared plus 2AB plus B squared. Why they are different? So I'm going to write A plus B square, which is A plus B times itself. Let's do here the multiplication, and be careful when you write the left and right matrices. So we'll get first A by A. I can write it as A squared. And then A by B. And then B by A. And then B squared. So this is the expansion of this guy. So it is not this one. Okay? Because in matrices, actually these guys are not necessarily equal, and they are not equal in this example. So this is not the same as this one. Okay? So this is the right expansion of the bracket. Suppose that I have three matrices, 2 by 2 square matrices, ABC, and let's find AC and BC. So AC, A to the left, C to the right, and do the multiplication. BC, B to the left, C to the right, and do the multiplication. Do you have any comment about the result? They are the same. So we have in this example, actually, we have AC equal BC. So in matrices, when you have AC equal BC, this does not imply necessarily that A equal B. Okay? As you see in this example, A is not B, but the product here is the same. So this, in general, does not imply that A equal to B. Again, later on, we'll see some condition when it is satisfied that AC equal BC would imply A equal B in some cases. Okay. Let's do here AB and BA. If you want to multiply A by B, is the product valid? Product valid? We have 3 equals 3, and the dimension of the output is 2 by 1. So the first entry would be 2 by 2 plus 3 by 5 plus 1 by 4. The second, 5 by 2, 4 by 5, negative 1 by 4. What about BA? مش هتنفع صح؟ BA does not exist from dimension point of view. So you can't find BA. BA does not exist. Do you have a multiplication identity? المحايد الضربي بتاعنا. احنا في السكيلرز عندنا ال1 ده الايدنتيتي بتاعنا. في الماتريسيز بقى بص كده لو جبت this matrix and multiplied by this guy. Ones on the diagonal. Okay? A square matrix with ones on the diagonal. If you do this multiplication using linear combination rule, so do linear combination of these guys using this entry. So you'll get the first column, and with this guy, you'll get the second column. So you get the same matrix. So we write it, for example, matrix A multiplied by identity, denoted as I, and it is a square, 2 by 2. We usually write it as I2. Okay? It's known that it is a square, so you don't have to write 2 by 2. Write just I2. And you will get the output as A. And we have a matrix, for example, 3 by 2. You can do left multiplication by an identity matrix, and it will be 3 by 3 for the multiplication to be valid. And we will get the same matrix B. So we say that I3 times B equal B. So this is our identity, and write it according to the dimension for the multiplication to be valid. So we have some properties on the multiplication. Okay. You can prove all of them using the linear combination rule. If you want to multiply matrices A, B, C in this way, we multiply B and C first, and then A times the result. You can do the product in each in different ways, such that you keep the order as it is. Don't change the order. So I can do A, B first, and then the output by C. The most important thing is to preserve the order of the matrices. Don't change the order. And if you want to multiply A by the sum of two matrices, you can distribute, as we do in the scalars, distribute A on the sum. So we'll get AB plus AC. And if you want to multiply a scalar by a product of two matrices, for example, 2 by AB, you can do the matrix multiplication first and then scale each entry with K, or scale the matrix A by K and then do matrix multiplication with B, or even scale the matrix B, because this is a scalar, so it can jump between the matrices, no problem. So you can do Ka by B or A times Kb. This is only for scalar. Okay? Move the scalar as you like. And this is for the identity a by I equal a and I by a equal m. And here I wrote the dimension for the multiplication to be valid as a is m by n. And as we said, a power n is defined to be a times itself n times for n integer, positive integer. So I want to find a power 8. So how many multiplication are you going to do? Multiply a by itself. So I'm going to do 7 multiplications. Is there a better way? We can give a square. حاجة better كمان. ممكن دي كده نجيبها مرة واحدة a power 4 and multiplied by a power 4 and so on. Okay? A multiplication for high powers, we do it simply by simplifying the product this way. Okay. Let's define an operation on matrices called matrix transpose. Matrix transpose, we simply just interchange the rows and columns of a matrix. So for example, if you have this matrix A 2 by 3, we write what is called A transpose, okay? And write the first row as the first column, the second row as the second column. So the dimension is going to be interchanged. Instead of 2 by 3, it would be 3 by 2. So this is the definition of the transpose of a matrix. We are going to use this extensively in this chapter and later on. So if you have, for example, this vector B, 3 by 1, so B transpose will be a row vector 1 by 3, 2, 4, and 3. Let's compute these guys. I want to find A times B and then transpose the output and transpose B and transpose A and do B transpose times A transpose. Would you please try it? AB and then transpose the output, transpose B and transpose A and do B transpose times A transpose. Okay, let's find first A times B and then do the transpose. So this is A and this is B. So the first entry here would be the dot product between these guys, right? It would be 2 by 2 plus 4 by 4 negative 5 by 3. And the second entry would be 1 by 2 plus negative 3 by 4 plus 2 by 3. Okay. Let's write the dimension here. We have here dimension 2 by 3, and this is 3 by 1, and this is 2 by 1. What about here? We have 1 by 3, and this guy 3 by 2, so the output here is 2 by 1. 1 by 2. What about the first entry here? Two times 2, 4 times 4, 3 times negative 5. The same? خلينا نكتب بنفس الطريقة بقى. 2 by 2 plus 4 by 4 plus 3 by negative 5. And the second entry, 2 by 1. And then 4 by -3. 3 by 2. So if you do actually the transpose of this guy to get AB all transpose, you will get the same answer like this one. Huh? So can we say in general that AB transpose equal B transpose A transpose? Okay. If you look at what we did here, actually this guy is the dot product between two vectors, 2, 4, and 3, which is this one, by the second one, 2, 4, and -5, which is this one. You will get here the same dot product between 2, 4, and -5, dot product with 2, 4, and 3. Okay? And the same for the second entry. So you can prove this in general. Okay? This is a numerical example, not a proof for it, of course. You can do it in general and prove that AB transpose always equal to B transpose A transpose symbolically. Okay? I'll leave it for you as an exercise to prove it in general that AB transpose equal B transpose A transpose. What about A transpose B transpose in this example? A transpose B transpose is not valid actually in this example. A transpose is actually here 3 by 2 and B transpose is 1 by 3. So this guy actually is not valid in this example. But this is a rule. AB transpose is B transpose A transpose. What about A, B, C all transpose? Equal to you can think of it as AB times C and apply this rule on this product. So it would be C transpose AB transpose, which is C transpose, and this guy is B transpose A transpose. So simply you just reverse the order when you distribute the transpose on each guy. Okay? Write it in reversed order. Okay, let's summarize the transpose properties here. What if I take the transpose twice? It will give the same matrix, right? A. What if you sum two matrices and then take the transpose? Is this equal to A transpose plus B transpose? I'm going to sum the two matrices and then get the transpose, change the rows and columns. Is this equal to A transpose plus B transpose? Let's say it in words. You here do the sum and then change the rows and columns. Here I'm going to change the rows and columns first and then do the sum. The same, مش كده؟ And as we said, AB transpose equal to B transpose A transpose. What about the scalar multiplication? If you have, for example, 2A transpose. What about this guy, 2A transpose? Are these the same? I'm going to scale each entry in the matrix and then interchange rows and columns. You can interchange rows and columns first and then scale each entry by 2. Okay, let's find these guys quickly. A transpose A and A transpose A and A transpose. Can you find the product quickly? So we have here A 2 by 3. If you multiply it by A transpose, which is 3 by 2, then the output would be of dimension 2 by 2. مش كده؟ If you multiply A transpose by A, this guy is 3 by 2, this guy is 2 by 3. The output is 3 by 3. So they are not the same, of course. Okay, they are of different shapes. If you try to do the multiplication, did you get this answer for A transpose? This guy for A transpose A. Right? Right. Did you notice anything about the result of these guys, A transpose A and A transpose? First, they are not the same, okay? They are both square matrices. Always square matrices. Always square matrices, مش كده؟ زي الexample ده. 2 by 3, you're going to multiply by 3 by 2, you'll get 2 by 2. So they are both valid. They are both square matrices. What else? If you do the transpose of the output, you will get the same matrix. مش كده؟ Let's write it for example here. If you have, for example, A transpose A. If you take the transpose of this matrix and apply the rule of the transpose. So I'll take the transpose of this guy first and then of this one. So the transpose of this guy is itself. Okay? If you look at the numbers here, you have some symmetry around the diagonal. Look at this diagonal, for example. You have here 5 and 5, negative 8, negative 8, negative. How can you benefit from this property? A equal A transpose? No, A does not equal A transpose. How do you benefit from this property in calculations? بس ممكن تستفيد ازاي؟ ان انت في الكالكوليشن بقى calculate بس these guys and these guys are the same. Okay? طيب. Let's define the last operation here, an operation called the trace of a matrix. Here the matrix must be square matrix. Okay? For the transpose, it's not necessarily to be square matrix. Okay? For the trace, the matrix must be square, and the trace is defined as the sum of diagonal entries. So if you have, for example, this matrix, this is called the main diagonal of the matrix. Okay? So the trace is the sum of these guys. You'll get a scalar called the trace of the matrix. So the trace for this matrix is 1 plus negative 3 plus 6, which is 4. Okay? We are going to use this operation in later on chapter 5, but we prefer just to introduce it with the other operation in this chapter. So let's find, for example, trace of the sum of two matrices and find the relation between the trace of the sum and the sum of the traces. Are they the same? Let's think about it. I'm going to find the sum of these two matrices and then find the trace, sum of diagonal entries. Or find the trace of each matrix and then sum the traces. You'll get the same scalar number. Let's do it symbolically. For example, if you want to sum A plus B, and this is your A, we want to sum it with matrix B. So we'll get the matrix A11 plus B11. What is the trace of this matrix? Sum of these guys, مش كده؟ A11 which is the sum of the traces, مش كده؟ Trace of A plus trace of B. So we can prove any property in the trace this way. And in this example, you find the trace is 8 in both cases. Okay? Okay. Would you please find these guys? 2 times trace of A, trace of 2A, trace of AB, trace of BA. And let's check if these guys are equal and these guys are equal. Can you find it quickly? عايزين بقى trace of 2A. A trace of this guy to be 2A11 plus 2A22, which is 2 times trace of A. This is in general. What about trace of AB and trace of BA? Are they the same? If you find A times B, you will get this matrix, and its trace is 4. BA, it would be another matrix with different numbers, but its trace is also 4. Is this always true? Trace AB equal trace BA. This is actually always true. I leave it for you as an exercise to prove that these guys are always the same. Trace AB equal trace BA. Although AB is different from BA, two matrices are different, but they have the same trace. What can you say about trace ABC? Equal trace. You can take this guy as a matrix. So this is equal trace C AB. All trace. You can take these guys as a matrix. So we'll get trace B, C, A. So is there a rule for these guys? Cyclic, to be cyclic. A, B, C. So ABC, trace ABC equal trace BCA equal trace CAB, and so on. They have the same cycle. So let's summarize the properties of the trace. The definition of the trace, as we said, is the sum of the diagonal entries, which is A11 plus A22 plus A33, or in compact form, summation of AII. Trace of the sum equal to sum of traces. Trace of Ka, and K is a scalar. You can take the K outside the trace. You can do K trace A. Trace of AB equal trace of B A. What about trace of A transpose? The diagonal remains as it is when you do the transpose, so it would be the same as the trace of A. Okay, finally, let's have a look on some special matrices, have special shapes, like these guys. We call a matrix is a row vector when it is 1 by n in general. So this is called a row vector 1 by 3. And this is a column vector 2 by 1. And we have a matrix with all elements are zeros. We call it a zero matrix, of course, of any dimension. Let's define what is called upper triangular matrix. We call a matrix an upper triangular matrix if it has zeros below the diagonal. So it is a square matrix first, square matrix with zeros below the main diagonal. Okay, so we call it is an upper triangular matrix, which means that the non-zero entries are on the diagonal and above. What about lower triangular? The opposite. You will get zeros above the main diagonal. Or the main entries, non-zero entries, are on the diagonal and below. So we'll call it lower triangular matrix. And it is, of course, square matrix. What about the transpose of a lower triangular matrix? You'll get an upper triangle. Okay? So the diagonal matrix, a matrix has non-zero entries on its main diagonal. Okay? Or in other words, zeros above and below the diagonal. Identity matrix is considered as a special case of the diagonal matrix. اللي هي I3 I2. طب if you remember symmetric matrix, لو قلنا بقى symmetric matrix, you have some symmetry around the diagonal. These guys are equal. So you can write it in symbols as A12 equal to A21 and A13 equal to 31. In general, Aij equal Aji. Or simply, as you said, the transpose of this matrix is itself. So we can write one equation for the symmetric matrix as a condition when you have A transpose equal to A. The last matrix is called the skew symmetric matrix, like this one. What do you notice about this one? Some symmetry, but with negative sign. So this guy is the negative of this one, this guy is the negative of this one. So we write it simply as A12 equal negative A21 and so on, or simply Aij equal negative Agi. To satisfy this condition for all entries, you will get for the diagonal entries, for example, A11 equal to negative A11, which means that A11 must be 0. The same for all the diagonal entries. So for the skew symmetric matrix, the diagonal elements are all zeros. What about the transpose of this matrix? If you take the transpose, do we get A? Write this row as first column, this row as second column, and so on. So we'll get the negative of A. So this is the condition of the skew symmetric matrix. The next lecture, inshallah, we're going to talk about the determinants and what is the relation between the determinant and the matrices. And then we are going to find the inverse of a matrix based on this lecture and the next one.